This next section, section 15.5, concerns musical frequencies. Okay, we've talked about the frequencies that these air columns and strings produce, and it turns out that if you look at other instruments, they do not produce frequencies for the overtones or for the other harmonics that are multiples of the basic ones. Why is that important? Well, it was discovered by Pythagoras first that sounds that sound consonant when their frequencies are nice integer multiples of one another. So, for example, you can show that for a drum or for a cymbal, you're really looking at a plate of steel or drum head. You do have frequencies that are multiples of the basic frequency, but you also have many frequencies that don't occur with strings and air columns that are things like the square root of 2 times the basic frequency. So these sounds sound ugly and discordant, or not consonant with, disconsonant with the fundamental frequency that it's playing. Consequently, things like drums are not used generally to carry melodies. Strings and air columns are used for that. Well, what is it that Pythagoras discovered? He did his experiment, let me first say, by taking a string, putting a weight on it, and adjusting the position of this point right here and plucking the string so that it ended up making different sounds. And he did that with 2 systems. So he did 2 of these at the same time and compared one of these with another that had a different length. So this is a length L2 and a length L1. Of course, what he found when he made this comparison was our previous result, that the frequency here would be equal to N times V over 2L, or N times F1. And down here he got the same result, but he got it for a different length. If the length down here is twice as great, or 3 times as great, or 4 times as great, then in fact you can see that, or say half as much, or 1/3 as much, or 1/4 as much, that it would be correspond to these various harmonics. Just like changing this integer and looking at the overtones. So this was a way actually to look at his first frequency, which was NV over 2 times L. And here, we're not looking at the higher harmonic so much as we're looking at the difference in length between one system and another. Again, as I said, if I take that first one, then I take a second one, F2, where I have N, and I'm going to choose N is equal to 1 in both cases. Velocity over 2 times L2. If this L2 is half the length, 3 times the length, 1/3 of the length, 1/4 of the length, then I'm going to get the overtones that would correspond to this frequency here, just like with higher Ls. And his conclusion was, the nicer the ratio of the 2 frequencies, the nicer the sound. In particular, unison is a 1-to-1. The 2 notes have the same frequency. An octave is 1-to-2. Now, I'm sure that all of you know what an octave is. And I have a very poor voice, but I'm going to attempt to try to explain what these sound like. An octave would be like da, 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 da. An octave is so consonant that we say that the jump of an octave is really the same note at a higher frequency. It's of course not the same note. It's just very consonant with that note. Now, the next most consonant is the concept of a fifth. A fifth has a ratio of 2-to-3. And you can see that 1-to-1 is the simplest, 1-to-2 is the next, 2-to-3 might be the next. And a fifth, when we listen to a fifth and the way it sounds, It's very easy to remember if you remember the theme song for the movie 2001. It jumps a fifth, and then it jumps the next time a fourth. So I'll go on and write down a fourth. A fourth is the ratio of 3 to 4. In other words, one frequency oscillates 3 times, the other one 4 times. Now, what is this fifth and what is this fourth? Well, the first jump you'll hear will be the fifth, then we'll jump a fourth, and the pair of them together turns out to be an octave. So it'll be da, 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 that's a fifth. Da, 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 that interval is a fourth. Da, da, fifth. Da, da, that's a fourth. And so now you know some of the most consonant of the intervals. So when a string is plucked or an air column is sounded, when these frequencies, when the various harmonics are stimulated, we hear the octave, we hear the fifth, we hear the fourth, even with a single string, because we're getting integer multiples of the basic frequency, even with a single note. And he proved that by looking at two strings and comparing the two. So Pythagoras taught us how to tune an early instrument. And if you are familiar with the piano scale, what we're going to do is go up a fifth and down a fourth and up a fifth and down a fourth. And so you kind of have to know this by having a very good musical sense. But if you imagine the notes on a piano, this would be the note C, the middle C, D, E. Of course, there are black notes here and here, none here, one here, here, here. This is F, G, A, B, and this would be C. So from here to here is an octave. From here to here, from C to G is a fifth. And from the G to the C again is a fourth. And these are the intervals that we have. So if you go up by a fifth, you'll notice that what you're really doing is going by 1, 2, 3, 4, 5, 6, 7 half steps. And if I go by a fourth, I'm going from G to 1, 2, 3, 4, 5 half steps. So early tuning of an instrument was done by the person's jumping up a fifth. So you go up to here, then you'd go down a fourth. So you'd go up 7, that's 1, 2, 3, 4, 5, 6, 7. And then I go down 5, 1, 2, 3, 4, 5. And so I get a D. So I go C to G, from G down to D, from D I would go up to here, so I'd get an A. From the A I would go down and get the E. From the E I would go up to the B, and now I have to be a little bit more careful because I have the half steps. So going up by a fifth, down by a fourth, up by a fifth, down by a fourth gives me the fundamental notes in the scale, and then I can play those, and of course you know what they sound like. In the major scale, playing only the white notes, we get da 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 da. Sorry about the voice quality there, but that's what I've got. Anyway, that gives us our piano scale, and you'll notice that overall this jump here is called a whole step, and this jump is called a half step to the black note. So I've got two half steps make one whole step. And altogether, if I look, I have 12 half steps. That's from the C to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 12 jumps. Or 12 half steps in an entire octave, something that we'll be using in just a few moments.